So let's do example number 3, which is based on impedance reflection. So we have an ideal transformer. Source voltage is 110 volt RMS, 60 Hertz. We have primary line resistance 1 ohm, primary line reactance 3 ohm, and generally line reactance is inductive reactance, so we have to represent it as J3 ohm. Secondary line resistance is 5 milliohm or 0.005 ohm, and likewise secondary line reactance is 0.02 ohm. A load is connected with resistance of 0.1 ohm and capacitor of 10 millifarad. So the first thing we're going to do is we find what will be the reactance associated with the 10 millifarad capacitor by using the relationship of reactance with the capacitor value, which is Xc is equal to 1 over j omega c. 1 over j omega c, so we are going to get negative 0.265 j265. Now observe, since we do not know the primary current or secondary current and primary voltage and secondary voltage, in this situation we cannot find these current or voltages out, and the only way to find it out is the reflection of one side on the other side. So in this problem, I'm just reflecting all the quantities that are present on the secondary side to the primary side. So R2, XL2, RL and XC are going to become R2 prime, XL2 prime, RL prime and XC prime. So let me go ahead and open Octave, and I'm gonna go ahead and copy this into a new file. This is example number 3, and then I'm gonna go ahead and put the values that I have. ES is 110, F is 60 Hertz, and R1 is 1, XL1 is J3, and turn ratio is 10, and R2 is 5 milliohm, 5 exponent negative 3. This is R2. Why do I keep doing that? This is XL1, and let's see, R2, XL2. XL2 is 0.02 I. RL is, what is RL? RL is 0.1, and C is 10 millifarad, 10 exponent negative 3. Okay. So first we're going to calculate Xc. Xc is equal to 1 divided by 2 times pi times F times C, so and times I. I is of course the imaginary number, and that will give us the value of Xc. And I'll just, to display the value, I'm not going to put the semicolon at the end. Okay, and I'll just keep it like that. Alright, now let's calculate the quantities that we are reflecting on the primary side. So R2 dash, R2, let's say prime, equals A square times R2, XL2 prime equals A square times XL2, and then RL prime equals A square times RL, and last XC prime equals a square times x. So that will calculate all of the values that are reflected on the primary side. Okay, so now it's pretty straightforward. All we have to do is to calculate primary current I1. We can apply Ohm's law with ES divided by ES divided by R1 plus XL1 plus R2 prime plus XL2 prime plus RL prime plus XC prime. So that's going to be my I1. Keep some space so everyone can see it properly. That's my I1. Secondary current I2. We know that the relationship between I1 and I2 is I1 over I2 is equal to 1 over A. So I2 will be equal to I1 over, or I2 over I1 is equal to A. So I2 will be equal to A times I1. I2 will be equals to A times I1. That's going to calculate I2. Next, load voltage. So the load voltage, when we calculate the load voltage over here across RL and XC, that's going to be the reflected load voltage. So it's going to be EL, or you know what, since we already calculated I2, the actual value of I2, we're going to go ahead and calculate the load voltage from the original circuit. So EL load voltage is equal to I2 times the load that is connected over there, which is RL plus XC. That's the load connected over there. That's going to be the load voltage. Of course, all these quantities are complex quantities, remember. So they will have a magnitude as well as an angular phase. Active power of the load. So active power of the load. Active power, remember, is only consumed in where? In the resistive part of the circuit. What we can do is we can calculate the complex power, and complex power will give us both active and reactive power of the load. The real part of the complex power is the active power and the imaginary part is the reactive power. So let's calculate the complex power. S of load is equal to EL times conjugate of the current that is flowing over there, which is I2. That's the complex power. And let me just make a remark over here. This is the complex load power. So that means the active power is going to be the real part of that, real of S load, and reactive power is going to be imaginary part of that, imaginary of S load. So that's my example number 3. Save, run. Let's see if there's an error or no. Yep, there's an error. Let's see. F. Okay, again I put in uppercase F and must be a lowercase f that I defined. Where's F? Right here. Right here. Let's go ahead and put lowercase f. Run it again, and everything is good. Or no, there's something that is not good. S load, lowercase load. Okay, S load. Run it again. Everything is good now. Okay, so XC is 0.265, negative 0.265 I. and then the reflected value of R2 is 0.5 ohms. Reflected value of line reactance is 2 ohm. R prime is 10 ohm. XC prime is 26.25. Negative, of course, because it's XC. So we calculated I1, we calculated I2, and again I'm calculating I1 and I2 here complex number, but when usually you give I1 and I2, it is given as magnitude and phase. Magnitude and phase. So make sure if you are solving it in the quiz or exam, make sure to convert this rectangular number into polar form. Load voltage is this. Again, make sure you give the load voltage in polar form. Complex power of the load, we calculated this. That means this is the active power, and negative 538 is the reactive power, and it is negative because, of course, the reactive power of the reactive part of the load is what? Capacitive. So this is how we can solve a circuit, transformer circuit, by reflecting one side to the other side, and we have to do that again if it is not given to us that what is the value of primary and secondary currents and voltages. So at that point we have to use this technique.